In this lecture, we will see a geometrical representation of the scalar product. I remind you that in lecture 10.2, which is the previous lecture to this one, we have shown that the scalar product between two vectors v and w in R2 equals the norm of the vector v times the norm of the vector w times the cosine of the angle theta between v and w. I remind you that the angle theta, by definition of angle between vectors, is bounded between 0 and pi. From this equality, we can link the scalar product with the projection, so-called projection, of the vector v along w, and also of the vector w along v. The word projection is ambiguous in mathematics. Sometimes it refers to a scalar, a number. Sometimes it refers to a vector, the relationship being that this scalar is the norm of this vector. But there is no standard choice between these two definitions. So we will settle for one definition that will be valid just for this course. Let's fix two vectors v and w in R2, v and w, and we define the projection denoted by pw of v, which is the projection of v along w, to be the vector constructed as follows. We draw the line connecting w with the origin, and in other words, this is the subspace of R2 generated by w, and we draw the perpendicular line from v to this previous line. So this is perpendicular. The intersection point between the red line and the green line is the projection of v along w. Now, it is a point in R2, therefore it is a vector. I remind you that points in R2 are element of R2 when we think of R2 as a geometrical object. But when we think of R2 as an algebraic object, meaning a vector space, then the points are called vectors. What is the relation between the scalar product of v and w and the projection of v along w? We need two extra equalities besides the one that we wrote at the beginning of the lecture, involving the projection of v along w. Now we need to consider two different cases in order to write these two equalities, because each is expressed differently according to the fact that the angle theta between v and w is in the range 0 pi over 2 and is in the range pi over 2 pi. The extreme is not important whether it is excluded or included, because in pi over 2 the two expressions that you write coincide. Therefore it doesn't really matter whether we include or exclude pi over 2 in any of these intervals. The first equality is as follows. It concerns the length of the projection, and this length can be written, the norm, can be written as the norm of v times cosine of theta if theta is between 0 and pi over 2. This is the case we are considering first. So let's draw again the situation as before, in which we define the projection of v along w to be such a vector. Now I've not written w yet because I will be moving the position of w according to theta being in this interval or being in this other interval. So the first case we will consider is theta between 0 and pi over 2, which is, for example, if W sits here on this line, we notice that theta then in this case is this angle, and by the picture that we are seeing here, theta is less than pi over 2. This equality comes from a basic trigonometry, according to which we can compute the length of this vector from the length of the vector v by multiplying the length of the vector v times the cosine of the angle theta. On the other hand, if W is, for example, on this other side of the line, then the angle theta is greater than pi over 2. So we are in this case, theta is between pi over 2 and pi. And if we just take the length of the vector v and multiply by the cosine of theta, we will be getting a negative number, because cosine of theta in this case it will be negative. The negative number we will be getting is exactly the length of this segment, negative sign in front. Hence we recover the correct equality expressing the norm of the projection by taking the opposite of the equality of the previous case. The second equality we will need is equality B, which relates this time the vector projection, not its norm, with this vector here derived by W. Again, we have to split in two different cases, the first one being the same as before, when the angle theta between V and W is comprised between 0 and pi over 2. So W is this side of the line, and we can express this vector as what? Okay, we take the length of this vector and we multiply by the unit vector obtained by W, which is pointing in the same direction as W. If W is as drawn here, and we divide W by its norm, we get a vector which sits on this line of length 1, and there are two of them, one on this side of the line, the other on the opposite side of the origin. If we divide by this positive number, the vector W, this vector will be sitting on the same side as W. So here, correct expression is to take the vector of length 1 on this line, but on this side of the origin, the same side as W, and multiply by the length of the vector projection. On the other hand, if W were this side, which corresponds to angle theta between pi over 2 and pi, if I were to take W divided its norm, once again the norm is positive, I will be getting the vector of length 1, but the same side of W, so it will be pointing this way. And if I multiply by any positive number, such as the length of another vector, I will be getting a vector this side of the line, and I will never be expressing the projection. Okay, so to fix this situation, just like before, we take the opposite, and by taking the opposite, we get precisely the vector P, projection of V along W. Combining the quantities A and B with the one that we wrote at the beginning of the lecture, we get the following expression. The projection of V along W can be written as a scalar, a big scalar here, which is the scalar product of V and W divided by the norm of W squared that multiplies a vector W. Let's comment a little further this equality. A scalar product between V and W divided by the norm of W we have seen to be equal to the norm of the projection, and this equality uses the expression A, the quality A, and the quality at the beginning of the lecture. Well, these at least when theta is comprised between 0 and pi over 2. We have seen that the equality A has two distinct cases, and because of that, using again equality A and the one at the beginning of the lecture, we see that this coefficient right here, for all the other cases of theta, is the opposite of the norm of the projection. Not really the norm of the projection, but the opposite of it. However, when we multiply on the right both of these terms, we see that these multiply on the right by this vector. Because of equality B, we obtain the projection vector of V along W. And when we multiply negative norm of the projection on the right by this vector, we get again the same vector projection, always by B, by the relation, by the equality B that we have seen before. The conclusion is that this equality holds without any assumption on V and W. So there is no distinction between theta belonging to this interval or theta belonging to some other interval. This equality will always hold for any V and W. In the particular case, the norm of W is 1, therefore this vector is W itself. We conclude that the projection of V along W is written in a particularly easy way, that is, the vector W multiplied by this coefficient that is just the scalar product between V and W. Therefore, this formula simplifies very much in the case the vector we are projecting V onto is a vector of unitary length. All we have said so far in the pictures we drew regard vectors in R squared. Both these yellow equalities and any other equality that we have written in this lecture hold more generally in Euclidean spaces of any dimension. Let's see now graphically how we recover these same relations in R3 using the fact that we have them in R squared. So what we are seeing here is the usual three-dimensional coordinate axis. We are in R3 and we have picked two random vectors V and W. If we just had to write the projections on V and W as vectors, this is what the result would look like. There will be just two other vectors here which seem totally unrelated to V and to W. Therefore, it is helpful to draw some supplementary figure here in this animation that will help us to understand how we can recover the projection of V along W and W along V from the situation in R2 that we have just seen. So let's first consider the plane that is generated by V and W as a subvector space. So it is the plane passing through the origin because it is a subvector space, and it is the set of linear combinations on V and W. I'm assuming here in this presentation that V and W are linearly independent. Therefore, there is a unique plane containing both V and W. If they were not linearly independent, we can just pick any plane containing both the vectors and the origin, and all the arguments that we have done before, since the angle between V and W would be 0, so theta would be 0, all the argument that we have seen just before they still hold, but they actually all collapse. Now we will think naively this plane to be the R2 plane that we have just seen a few moments ago. Okay, so let's just change the point of view in order to reproduce the same constructions that we have just done, and we can see them better in R3. Our vector V and our vector W. You remember that the projection of V along W involved drawing lines passing from V to the origin and from W to the origin. Now we replace the lines with these arrows, and the reason why we draw arrows instead of lines has to do with the fact that we consider V and W to be vectors, and I always recommend not to write vectors as arrows, and the reason for that will be explained in a future lecture. But when we want to draw and we want to represent angles between vectors, we are somehow forced to add some extra objects in the picture in order to visualize the angle. Without lines or segments, we cannot visualize any angle. This is the projection of V along W, and this is the orthogonal line passing from V, orthogonal to the line passing through W. The intersection point is the projection vector of V along W, as we have seen previously in the two-dimensional case. We represent it just like any other vector we have done in this animation. We draw an arrow starting from the origin to the projection, again just like we have done here for the vectors V and the vector W, to emphasize that the projection is considered to be a vector in this case. Now, identifying this plane, we can identify this plane with R2 by means of an isometry, but we are not going to talk about this. In any case, by this picture, we can prove that this vector here can be represented exactly in the same way as we have seen for R2 case. So we take W, this is the only vector components of this expression. Everything else are just numbers. So we take W, we divide by its norm, getting some unit length vector on the line connecting W with the origin. So the vector space generated by W, and it will be in the same side as W. So in this case, it will be in this side. And then we multiply this unit vector by this number right here, which is derived by the formula that we have just seen before. So this vector has this representation just like in R squared. And this, finally, is the projection of W along V. We connect W with the line passing through V and the origin by taking the normal line passing through W and the intersection point with the line passing through V. We make this, we represent this as a vector, and we rewrite it, the formula that we have seen here, but replacing W with V, because we are projecting W along V and not vice versa.